So let's try to get the distribution of the price process at time t. So it's not going to be too difficult. There's a couple different ways of thinking about this. On one hand, you can kind of ignore this positive part operator and just kind of get a handle at what you do know. So B is a standard Brownian motion. At time t, it has a normal distribution with mean 0 and variance t, as on the left. Now what happens when you multiply it by sigma and add an x? So I've defined as w sigma x at time t as that variable. W sigma x is now going to be a Brownian motion started at x with volatility sigma. And here you just kind of follow the basic rules about what happens when you multiply normal random variables by scalars and add them. So basically linear functions of random variables. If you multiply by a scalar, multiply a normal random variable by a scalar sigma, you just pick up that sigma as squared in the variance. So it doesn't affect the mean, but it does affect the variance. And then adding x will not affect the variance, but it will shift the mean over to that point. So so therefore we just directly conclude that w sigma x at time t has this density. This is the density of a normal random variable with mean x right there, and variance sigma squared t. This is the density sort of drawn out, the usual bell curve that we know about, and this would be, I guess, all the points would sort of lie within 1 or 2 standard deviations, or most of the probability masses within 1 or 2 standard deviations. The standard deviation here is sigma times the square root of t. And so if you wanted the cumulative distribution function of sigma x at time t, like here you could, on one hand you could just integrate this from here up to whatever the upper limit is. Here's w. So that's one way, and another way of thinking about this is starting from here, take both sides of this expression, subtract an x, and divide by sigma. You'll get this probability here in terms of the Brownian motion. This is normal mean 0 variance t, and so it just comes down to writing it down as this integral. This is the cumulative distribution function of a normal random variable. It has variance t, mean 0, and the upper limit where we're evaluating this cumulative distribution function is wx over sigma. Probably a useful exercise would be to kind of change variables here and relate it to an integral over this density here. So I'm going to suggest to you that the right change of variables is this one here. You want to have the integrand here look more like that density, so why not just take this z squared and replace it by what it should look like, which is y minus x squared over 2 sigma squared t. That's exactly what you'll get if you make this change of variables. And now you just need to fix the limit, which will end up being w, and you'll need to fix the variable over which you're going to be carrying out the integration, which in this case is going to be y. So you'll need to relate the dz and the dy, and in here dz is going to be equal to dy over sigma. That's what's going to give you that's what's going to have you pick up the sigma in the denominator here, as you see it here, but you don't see it there. So now we get to the final kind of part, which is what about the cumulative distribution of the price? This is sort of the more important part. I've drawn it here. Let's kind of see why this picture makes sense. So this would be f of x. This would be f, the cumulative distribution function of xt, the price at time t. So one thing you can kind of ask is, what is the value of this thing? What is the probability that x of t is smaller than some negative number? Well, x is at least 0. This is what that positive part is doing. And so if the if x is non-negative, how can it be less than a negative number? It can't be by definition. And so I've just broken it, separated this case out and said, look, the cumulative distribution, the CDF, is just 0 below any negative number. So what's the next case? You can kind of break it down step by step and say, how about the point 0? What happens here? Well, here we're asking what is the probability that the price is 0? What does that say about, say, the process W sigma x? Well, if W sigma x is negative, then this positive part will lead us to x being 0, meaning the price being 0, and you should be able to convince yourself of the fact that the probability of that is the integral from minus infinity up to the level of 0 of this exact density. In other words, this shaded area here, the area under this curve, this is the entire probability with which the price itself, which is zeroed out if W sigma x is negative. This is, this probability here corresponds to our price being 0, right? Z equals 0. So x less than or equal to 0 is basically the same as x equal to 0, because anything below will give us a 0 probability. And so you kind of can start plotting the CDF here. I've sort of marked I've defined this number p0, the probability that the price at time t is 0. We know that it's this integral, the area of, under this curve up to 0, and I've kind of marked it on this plot here. We know that the CDF is going to, assume this point at z equals 0. So z is on this axis here. So that's the beginning, right? I've gotten like half credit on this so far. I know that the CDF is 0 to the left of the origin, and I know that at the origin I'm just going to pick up a probability that the price is equal to 0, which is clearly a positive number. It's the area under the curve to the left of the origin here. And the rest is whatever this distribution tells me, right? Anything, continuing kind of computing the area under the curve and going further and further up to some point z. So if z is positive, I'm going to draw it on this side, then integrating everything under this curve up to z will give me whatever number I'm looking for here. So if my z is here, this point here would just be the integral under the curve up to up density all the way up to the value z, and so on and so forth. And that's just that's exactly what I've written here. Another way to say this is to break up that integral into two parts. The one that carries out the integration up to the origin, so p0 is the area shaded to the left, and then the remaining part of the integral from 0 to z, the integral that carries out from the origin up to z, computing this area here. And of course, as z goes to infinity, you better approach 1, which is exactly what should happen here. This, right, is not quite, you can look at this distribution and you note that it's not quite the CDF of a normal random variable, because it jumps here. A CDF of a normal random variable would continue kind of, first of all, smoothly, right? It would smoothly, decay down to 0. Here, because we've taken the positive part, it results in this jump. This is what this open circle indicates. There's no value here. The value at the point at the origin is up here, of a positive number, and in fact, there's no density around this point. So this CDF is not differentiable at the origin, and therefore the density of this random variable doesn't exist at the point, at the origin. It exists everywhere else. So here the function is differentiable, and the density, for any point z greater than 0, the density just corresponds to the one that W sigma x had. But at the value 0, there really isn't going to be any density because of this discontinuity here. And then again, to the left, you actually do have a density. The derivative of 0 is just 0. So now the density kind of just flattens out and goes back to 0. And because of this discontinuity, there's no density in our price process at the origin. So the next thing we want to look at is what this means for our options contract, and how do we kind of make a decision as to whether to invest or not, to buy the contract or not.